Wood needs no introduction. Since the dawn of civilization, it has served as humanity's foundational building material, and arguably, our success as a species is owed to its unique cellular structure that creates exceptional strength relative to its weight. However, when wood is used as an engineering material, its biological properties are exposed as limitations. In its natural form, it's structurally unpredictable, dimensionally unstable when exposed to moisture fluctuations, and strictly limited by the physical dimensions and biological defects of the tree from which it's harvested. But by systematically deconstructing wood into its constituent components and then reconstructing it, a highly predictable, mathematically quantifiable composite material capable of competing with steel and concrete in the modern built environment emerges. This is the story of engineered wood. The vast majority of commonly used engineering materials are considered isotropic. They exhibit identical physical and mechanical properties regardless of the direction in which a load is applied. Wood, however, is anisotropic, varying in physical response drastically depending on the direction of the applied force relative to the grain. This is a direct result of its internal structure, which in effect can be characterized as a tightly bound bundle of microscopic hollow straws with the cavities known as the longitudinal cell lumina. Because of this highly directional structure, wood possesses three principal anatomical axes. The longitudinal or axial direction runs parallel to the grain, running vertically up and down the trunk of the tree. The radial direction, which runs perpendicular to the growth rings, pointing outwards from the center pith to the bark, and the tangential direction, which forms a tangent to the curvature of the annual growth rings. In the longitudinal direction, the tubular cell structure creates exceptionally high compressive strength, though in the transverse direction, these hollow structures lack reinforcement and are highly susceptible to crushing, shear, or splitting when perpendicular forces are applied. Beyond its mechanical characteristics, wood's other physical properties are also highly directional. Moisture transport, for example, is primarily driven by capillary action through continuous cell lumina. Because these pathways run parallel to the tree's growth axis, liquid wicking is highly directional. Wood absorbs liquid through its end grain anywhere from roughly 100 to over 10,000 times faster than through its face or edge grain, with the ratio varying considerably by species. Electrical conductivity also follows a similar anisotropic pattern, with current propagating parallel to the grain with roughly 2 to 3 times the efficiency as it does perpendicular to it. Wood is inherently a hygroscopic material as it exchanges moisture with its environment in response to the ambient temperature and relative humidity of the air. Water exists within the cellular matrix of wood in two distinct forms: free water, which occupies the hollow cell cavities, and bound water, which is molecularly bonded within the physical structure of the cell walls themselves. A wood's moisture content, or MC, is the relative weight of water within it when compared to its oven-dried weight. On a freshly felled green tree, this can range from approximately 30% to over 250%. This variability exists not only between different species, but also within individual trees. In living softwoods, the moisture content of the outer sapwood is usually significantly greater than that of the inner heartwood, whereas in hardwoods, this moisture differential depends heavily on the specific species. As green timber is dried, the free water located in the cell cavities separates first, evaporating at a relatively fast rate. Eventually, the wood reaches a critical threshold known as the fiber saturation point. This is the exact point at which the cell cavities are completely empty of free water. But the cell walls remain fully saturated with molecularly bound water. For most woods, this occurs at around 30% moisture content. Above the fiber saturation point, the macroscopic physical and mechanical properties of wood generally do not change. However, once below it, the removal of bound water causes the cell walls themselves to physically shrink. This shrinkage is highly anisotropic and is greatest in the tangential direction at a magnitude roughly twice that of radial shrinkage, with longitudinal shrinkage being negligible. The combined effect of this shrinkage distorts the shape of the material, causing it to cup, bow, and twist depending on how the annual rings are curved within the specific cut of the board. This problem is further compounded by the outer surface of the lumber drying much faster than the wet interior core. As the surface moisture content drops below the fiber saturation point, the outer shell attempts to shrink, but is physically restrained by the swollen, wet interior. This creates large internal moisture gradients and nonlinear shrinkage behaviors, inducing structural stresses that lead to surface checking, splitting, and internal cracking. Beyond its physical properties, lumber is also limited by the very nature of being a living organism. As trees grow, the branches it produces appear as knots during milling. Knots are highly problematic in structural applications as they sever the continuous, load-bearing longitudinal fibers of the wood. They act as severe stress concentrators that dramatically reduce the tensile and bending strength of a solid beam and make its failure point unpredictable. Environmental stresses during the tree's life, such as prevailing winds or growing on a steep slope, also cause the tree to form reaction wood, known as compression wood in softwoods and tension wood in hardwoods. Trees also produce juvenile wood near the center pith during their early years of rapid growth. These structural deviations create excessive longitudinal shrinkage of up to 2% from green to oven dry. Because longitudinal shrinkage is typically insignificant, at around 0.1 to 0.2%, this localized section of longitudinal overshrunk material can cause catastrophic bowing and render the beam structurally useless. Beyond defects, the sheer physical size of a solid timber beam is strictly limited by the diameter and height of an available old-growth tree. Building massive structures using smaller, more readily available trees required completely new approaches to using lumber. By the dawn of the 20th century, the architectural demand for massive, clear-span structures exceeded the dimensional capabilities of solid sawn timber. Structural steel and steel-reinforced concrete were rapidly becoming the materials of choice for these engineering projects. To remain competitive, wood had to be entirely freed from the dimensional limits of the log. One of the first engineered lumber solutions to push past this limitation was developed by 1901 and subsequently patented in 1906 by German carpenter, sawmill owner, and structural engineer Otto Karl Friedrich Hetzer. Hetzer conceptualized the process of slicing timber into thinner boards or lamellae, removing the most egregious natural defects and bonding them back together under pressure to form large composite structural members. These composites were originally called Hetzer binders, but today they're more commonly known as glue-laminated timber or simply glue-lam. In Hetzer's method, the sliced lamellae are visually sorted, graded, and strategically staggered. A knot that might ruin a solid beam is localized to a single thin lamina, with an adjacent flawless lamellae being chosen to bridge the gap and maintain the beam's overall structural integrity. The sorting and grading is also used to determine material placement in order to match a target stress requirement. For example, in a horizontal roof beam, internal stresses are highly uneven, with the top edge being under heavy compression and the bottom edge under tension, and the center being a neutral axis. By positioning high-strength premium timber on the outer top and bottom edges to handle the intense forces, while filling the center core with cheaper lower-grade wood, the beams are cost-optimized. In some specialized applications, he even combined different species, utilizing dense beech wood for the compression zone and straight-grained spruce for the tension zone. One of the biggest advantages of Hetzer's process is its geometric flexibility. Because the individual lamellae were cut thin and remained highly pliable before the adhesive cured, it could be bent over massive forms and clamped into sweeping arches. The thickness of the individual lamellae was mathematically sized to meet the needs of the curve, and once cured, the beam maintained the curved shape permanently, allowing for structures that once required steel supports to be made purely in lumber. In the bonding process, Hetzer used heavy mechanical screw presses with a non-waterproof casein-based adhesive that was produced from milk proteins. Hetzer kept the exact recipe for his glue a closely guarded industrial secret well into the 1950s. Upon its introduction, exhaustive load testing conducted had empirically proved that these glue-laminated beams could withstand significantly higher forces than similar beams made of solid timber. By 1910, the Reichseisenbahnhalle, an immense pavilion constructed using Hetzer's arched glue-lam frames, would be exhibited at the Brussels International Exposition. The structure boasted an unprecedented free span of 43 meters with composite cross-sections measuring nearly 3 meters high. The material had proven to offer significant economic advantages over steel, particularly in aggressive environments that corroded iron trusses. By 1925, over 20 companies across different countries had purchased the lucrative rights to utilize Hetzer's patent. Norwegian engineer Guttorm Brick acquired the original patents and bought the technique, including the secret glue recipe, to Scandinavia. His Swedish factory notably supplied the sweeping, durable glue-lam arches for major railway stations in Stockholm, Gothenburg, and Malmö. Glue-lam's adoption surged again during World War II, eventually leading to the creation of U.S. manufacturing standards by the 1960s. The introduction of fully water-resistant adhesives like phenol resorcinol formaldehyde or PRF resin and melamine urea formaldehyde or MUF resin enabled glue-lam to be used in exposed exterior environments without concern of glue line degradation. Today, modern glue-lam engineering has evolved significantly, utilizing structural finger joints to create beams of practically any length and CNC machining to craft highly precise, complex architectural shapes. Even as we break free of the limitations of raw timber, we still have to actively protect and restore the natural ecosystems that make the sustainability of this incredible natural resource possible. If you're looking for a way to actually make a difference right now, you need to check out what my friends at Planet Wild are doing. Planet Wild is a community-driven nature protection organization. Think of it as crowdfunding for nature. Every month, their community of over 20,000 members funds new, carefully selected missions to bring back endangered species, protect our oceans, or restore forests. They don't just show you environmental problems and stop there. They enable actionable solutions that you can directly observe. Because you can literally see the impact of your community contribution in less than 30 days as they document every mission right here on YouTube. For example, they've partnered with American Prairie to restore the American Serengeti. By removing old cattle fences, they're helping to reintroduce iconic wildlife like bison and pronghorns to reclaim millions of acres of forgotten grasslands. In another mission, they actually brought the Planet Wild community out into the field in Belgium to help restore ancient peatlands. They worked to fill in long drainage ditches and remove non-native trees, which stops decomposition and keeps carbon locked safely on the ground. I became a member myself because it's easy to feel helpless about the state of our planet, but seeing this community in action actually gives me hope. With Planet Wild, you can make an impact without having to be on the ground yourself. You get monthly videos and text reports to see exactly what your contribution achieves, plus a badge for every mission you support. If you're looking to become part of an expanding community that's actively restoring our environment, you should definitely look into joining Planet Wild. You're free to contribute any amount that works for your budget, whether large or small. Every single dollar helps protect our natural world. I also have a special offer. I'll cover the cost of the first month for the first 100 people who sign up using my code MIND4. To grab this gift, just scan the QR code on the screen or click the link down in the description. Your contribution will make an immediate impact, and you get to see exactly what you helped achieve in under 30 days right here on YouTube. Plus, there's absolutely no catch. You can cancel your membership whenever you want. If you want to see Planet Wild in action, check out their YouTube video showing how they revived the American Serengeti. I'll link the video below. Beyond linear structural use, wood also suffers from severe anisotropy in thin, planar applications. Solid wood board, no matter how carefully selected, still splits easily along the longitudinal grain and undergoes massive tangential shrinkage across its width. To create dimensionally stable wide panels, modern structural evolutions of the cross-lamination process are used. In cross-lamination, wood is peeled radially into extremely thin veneers and glued together in a layup with an odd number of layers, where the grain of each alternating layer is typically rotated 90 degrees to the adjacent layer. This process, which forms modern plywood, eliminates the inherent weakness of one layer by counteracting it with longitudinal tensile strength of the adjacent perpendicular layer. The negligible longitudinal shrinkage of the cross-banded layers also physically restrain the high tangential shrinkage of the core layers, resulting in a panel that is dimensionally stable, warp-resistant, and quasi-isotropic. While the concept of cross-laminated wood, primarily for aesthetics, dates back millennia across multiple civilizations, it would take World War II to transform plywood from a decorative covering into a mass-produced structural material. During World War II, the U.S. Navy urgently needed fast, heavily armed patrol boats for the Pacific. In the pursuit of speed, ease of field repair, and light weight, the Navy hosted a 1939 design competition, culminating in an endurance trial called the Plywood Derby. From this, Elko, Higgins, and Huckins would go on to produce hundreds of PT boats incorporating highly specialized marine-grade plywood that could handle naval combat demands. The lower hulls used a composite composed of 2 layers of double diagonal Honduran mahogany planking that sandwiched a layer of canvas impregnated with marine glue. For the decks, bulkheads, and superstructure, Marine-grade plywood crafted from premium mahogany or Douglas fir veneers was used. These veneers were cross-laminated and bonded under extreme heat and pressure using waterproof phenol formaldehyde or resorcinol formaldehyde resins. Soviet naval engineers pushed composite technology even further with their Project 183A torpedo boats. These vessels featured an incredibly tough outer skin made of arctilite. This early structural composite bonded alternating layers of birch veneer and fine steel wire mesh using a heavy alcohol solution of phenol formaldehyde resin, curing into an exceptionally rigid, impact-resistant hull. In aviation, the British de Havilland Mosquito pushed the capabilities of plywood even further. Dubbed the Wooden Wonder, its fuselage was made from a composite sandwich construction composed of lightweight Ecuadorian balsa wood core bonded between thin outer layers of Canadian birch using urea formaldehyde adhesives. Because this true monocoque shell carried structural loads directly, it eliminated the need for heavy internal metal framing and also reduced parasitic drag by eliminating the need for rivets. Even more technologically ambitious was the Hughes H4 Hercules. Referred to as the Spruce Goose, it was built primarily of yellow birch. In order to achieve the strength-to-weight ratio required for the massive aircraft without using restricted aluminum, a process known as Duramold was used. Developed by Virginus E. Clark in the late 1930s, the Duramold technique involves impregnating birch veneers, often as thin as 1/32 of an inch, with phenol formaldehyde resin. These plies were meticulously stacked with alternating grain directions into complex mold forms, and then the assembly was sealed within a massive autoclave and subjected to temperatures around 138 degrees Celsius or 280 degrees Fahrenheit and pressures up to 6.9 bar or about 100 psi. Polymerizing the resin, chemically and mechanically locking the wood fibers into a stiff, monolithic structural matrix. The techniques developed from molding complex 3D plywood forms for wartime applications heavily influenced post-war design. Renowned American designers Charles and Ray Emis, who spent the war developing lightweight stackable molded plywood leg splints for the U.S. Navy, translated the bending and curing of cross-laminated veneers into the distinctive look that enveloped mid-century modern furniture. The rapid advancement of engineered wood materials was primarily driven by the mid-20th century shift from natural biopolymers to synthetic thermosetting resins. The introduction of synthetic resins such as phenol formaldehyde, urea formaldehyde, and polymeric diphenylmethane diisocyanate created chemically inert bonds that often became stronger than the physical cellulose wood fibers themselves. While wood adhesion can be categorized into 7 primary models, modern adhesives relies primarily on a combination of these concepts with a greater emphasis on the key mechanisms of mechanical interlocking and chemical bonding. Mechanical interlocking takes advantage of wood's highly porous biological structure. When a liquid synthetic resin is applied, it flows into the wood's microscopic pores and cell lumina. As it cures under heat and pressure, it hardens into thousands of microscopic solid polymer hooks. This physical integration provides resistance to shear forces and stops cracks from spreading. Viscosity control is a large factor of mechanical interlocking. If the resin is too thin, it penetrates too deeply, starving the bond line of adhesive. If it is too thick, it fails to grip the pores, limiting the depth and strength of the interlock. Laminated products typically require higher viscosity resins to prevent overpenetration, while composite strand products require lower viscosity to ensure the resin effectively coats the vast surface area. While mechanical hooks provide physical strength, the most robust bonds rely on chemical adhesion at the molecular level. Covalent bonding occurs directly between functional groups in the adhesive and atoms on the wood surface. Because wood is rich in cellulose, it offers abundant exposed hydroxyl groups. Modern adhesives, like polymeric diphenylmethane diisocyanate, are explicitly engineered to seek out and react with these groups, forming irreversible covalent urethane linkages. To boost this effect, chemical coupling agents such as hydromethylated resorcinol are used on tougher-to-bond woods to enrich the surface with chemical anchor points, maximizing the final bond strength. All adhesives must account for the hygroscopic nature of wood. If the cured adhesive is too brittle or expands at a different rate than the wood, mechanical stresses build up at the bond line. Moisture can also attack the polymers directly. Common interior urea formaldehyde resins, for example, can depolymerize under heat and humidity, releasing formaldehyde gas and shattering the joint. In contrast, thermosetting resins like phenylformaldehyde resist plasticization and hold tightly to wood fibers even when completely saturated with water. After World War II, engineered wood products expanded rapidly within the construction industry as a cost-reducing solution. By 1969, the first wooden I-joist would be introduced as the first true mass-market replacement for solid lumber in residential construction. Developed by Art Troutner and Harold Thomas of the Truss Joist Corporation, the concept applied the engineered logic of steel I-beams to timber. Troutner's earlier open web truss design had used 2x4s fastened to steel tubing, but the 1969 wood I-joist refined this into a fully timber-based assembly. High-grade solid lumber formed the narrow top and bottom flanges to handle primary stresses, connected by a deep, thin web of structural plywood. This design used a fraction of the material of solid beams while being lighter, perfectly straight, and capable of clearing much larger spans. These engineered assemblies also improved seismic and wind resistance, as the plywood web could resist shear and cross-grain tension during diaphragm rotation far better than traditional wood. Despite these advantages, early I-joists were still limited by the natural defects of the solid wood flanges that could compromise the tension zone. The industry sought to move towards higher material predictability and further cost reduction. Around 1970, the company introduced Microlam, its proprietary laminated veneer lumber product, which became the first fully engineered wood to replace traditional lumber in structural applications such as beams and headers. This marked the commercial emergence of an entirely new category of materials known collectively as structural composite lumber, or SCL. In structural composite lumber, logs are peeled into thin veneers or sliced into controlled strands. With the wood broken down to a near fiber level, it is coated in synthetic resins and pressed into massive billets, creating material free from warping, bowing, and splitting. These billets are subsequently resawn into specific dimensions based on end use. Because of their high predictability, structural composite lumber products can be standardized, with ASTM D5456 serving as the primary evaluation framework for the category. They are also easily classified by the geometry of their wood elements. Laminated veneer lumber, or LVL, is created from thin veneers layered with parallel grain. Depending on the grade of lumber it replaces, LVL allowable bending stress values can run roughly 1.5 to 2 times those of standard dimensional lumber. Parallel strand lumber, or PSL, is made from long, clipped veneers at roughly a 300:1 length to thickness ratio, providing the high strength needed for heavy-duty columns and headers. Laminated strand lumber, or LSL, and oriented strand lumber, or OSL, utilize flaked wood strands of varying lengths at 150:1 and 75:1 length to thickness ratios, respectively. These are commonly used for rim boards, tall wall studs, and headers where dimensional stability is paramount. As structural composite lumber began to redefine linear structural framing, a transformation of the structural paneling industry was simultaneously occurring. For decades, the structural panel market was dominated by plywood. However, high-quality plywood fundamentally relies on large-diameter, high-grade peeler logs to create clear, wide, continuous veneers. A method to create high-performance structural panels from small, crooked, knotty, and previously unusable, fast-growing tree species such as lodgepole pine, aspen, and poplar was needed. The solution to this would emerge as oriented strand board, or OSB. While first produced in Canada in 1964, OSB truly achieved market dominance in the mid-1980s. Instead of peeling continuous veneers from a massive log, OSB manufacturers utilized disc or ring-type flakers to slice small-diameter logs into millions of rectangular strands. These strands are dried, mechanically mixed with waterproof synthetic resins and emulsion wax, and then formed into thick mats. The OSB manufacturing process effectively mimics the cross-lamination principle of plywood, but on a smaller scale using discrete strands. A huge technical leap in OSB production would occur in 1974 when researchers from Potlatch Forests Incorporated and Washington State University developed electrostatic wood strand orientation techniques to supplement traditional mechanical alignment methods. In OSB, the strands in the two outer surface layers are highly aligned parallel to the long direction of the panel to maximize longitudinal bending strength and stiffness, while the strands in the internal core layer are arranged perpendicular to the surface layers, providing the critical cross-lamination needed to resist transverse warping. The entire thick mat is then subjected to heat and pressure in a multi-opening press that operates at temperatures of 205 to 220 degrees Celsius or 400 to 425 degrees Fahrenheit, and pressures of 4.5 to 5.5 megapascals or 650 to 800 psi. As the thermosetting resins cure, it chemically locks the interwoven strands into a solid, highly uniform structural building panel. By engineering the geometry and orientation of the strands, OSB achieves considerable structural efficiency, matching or exceeding traditional plywood in shear strength and uniformity. However, plywood does retain an advantage in bending stiffness and moisture resistance, as OSB panels are more prone to edge swelling and slower to recover after wetting. Still, OSB's ability to deliver strong structural performance from fast-growing, small-diameter timber at lower cost has made it the dominant sheathing material in modern light-frame wood construction. For most of the 20th century, large-scale commercial and high-rise construction remained the exclusive domain of structural steel and reinforced concrete. By the 1990s, European engineers would devise methods to produce an entirely new category of timber-based structural materials capable of replacing traditional materials in a building's primary load-bearing structure. Collectively known as mass timber, the technology is composed of several distinct products. Nail-laminated timber, or NLT, is one of the oldest methods and stacks dimensional lumber boards on edge and fastens them with hundreds of metal nails. Though structurally adequate, the embedded metal makes NLT incompatible with CNC milling equipment. Dowel-laminated timber, or DLT, solves this by eliminating metal entirely. Softwood boards are friction fit together using transverse hardwood dowels, dried to a lower moisture content than the surrounding lumber. Once inserted, the dowels absorb ambient moisture and swell, permanently locking the assembly. Because DLT is all wood, it is fully CNC machinable, enabling complex curves and acoustic profiling to be cut directly into structural panels. By far the dominant product of the mass timber revolution is cross-laminated timber, or CLT, a prefabricated solid panel typically built from an odd number of layers of solid sawn lumber bonded under pressure with structural adhesives. Each alternating layer is oriented at exactly 90 degrees to the one adjacent to it. This cross-lamination simultaneously achieves two-way structural spanning capability and dimensional stability, as the negligible longitudinal shrinkage of the outer layers physically restrain the higher tangential and radial shrinkage of the perpendicular inner layers. This orthogonal layering, however, introduces a critical structural vulnerability known as rolling shear. When a cross-laminated timber floor panel deflects under gravity loading, shear stresses must transfer between layers. In the cross layers, these forces act perpendicular to the wood's longitudinal grain, directly across the weak radius tangential plane. Wood is highly resistant to stress along the grain, but when force is applied laterally, the hollow cellulosic cells roll over one another and progressively rupture, a failure mode entirely distinct from conventional shear fracture. Accurately modeling this behavior requires engineers to move beyond simple beam calculations and into a far more complex framework known as Midland plate theory. This model allows the capture of the transverse shear deformation that occurs in thick, layered panels, which creates the condition that makes rolling shear in cross-laminated timber so consequential. Mathematically, cross-laminated timber is significantly weaker in shear than its size and weight would suggest, so conservative correction factors must be applied to keep designs safe. Engineers must then run a final worst-case stress check confirming that the combined forces acting on the panel at any point stay within what the wood can physically handle. For a typical structural timber grade, that rolling shear limit is remarkably low, making careful design planning critical to using CLT safely in high-rise construction. The future of engineered timber will likely involve the manipulation of its fundamental properties through nanoscale transformation. Engineered wood may fundamentally redefine the future limits of sustainable architecture and advanced material science. Quick reminder because it's so important. If you want to help fund real-world nature restoration, click the link in the description. Don't forget to use code MIND4 so the first 100 of you can get your first month completely free. And if you want to see Planet Wild in action, check out their mission rebuilding the American Serengeti right here.